Testing. Testing. Is this working?
Yeah, I can hear.
Yeah, we need to. We're running a little late here.
Okay.
Is it good?
Say something.
Okay, I'm saying something. Is it coming through?
Okay. Patricia, and
Okay, so you hold in the mute button. It's really the only real button on here.
oh, it's on everything
And then
else.
it takes like 5 or 6 seconds. So yeah, you should be good.
Cool.
And that should be working. I think everything's in place here.
And how are we doing in terms of time? Right on?
Oh, well, it's 1 minute past. Oh, no, we're 1 minute late.
Okay. Well, thank you all so much for coming to the North Houston Space Society. We have a few people online, so if you have a question, just raise your hand and we'll bring a mic to you so that the people online can hear you. So first of all, if you're not already a member of the North Houston Space Society, I recommend you all join us. You can scan that QR code. And you may be wondering, why would you join the North Houston Space Society? So I am here to answer that question. You get access to our Slack channel that lets you connect with other people interested in space and participate in events and things like that. We do tours and outings. That right there is the Bishop airlock, which is now on the International Space Station. So we actually got to touch a piece of space hardware that's up there. And we went to this DynaQual lab to see how they do dynamic qualification testing. And then we went on a tour of the Infinite as well. So that's kind of cool. And then we do outreach events. So we went to Comet Palooza where we interacted with hundreds of people. It was a lot of fun. And then we also do judging for the Science and Engineering Fair of Houston. And then of course you can vote for officers and become an officer and other club business. So anyway, welcome everybody to join us. And then the other thing is, let me go over the agenda for the day. So tomorrow we have an exciting event, which I'm sure you'll hear more about in the meeting. But we're going to start off by going over some space weather that's happening. And then there's a new comet in the sky, which Brooklyn's going to tell us about. So I'm excited about that. And then Greg's going to give us an update on space news, which I think we'll talk about the events of tomorrow, perhaps, maybe. Okay, and then our feature speaker is we got Michael Flores here, so really glad to have him. And then we'll look at ending about 4 o'clock. And if you hadn't got enough of all of us and you want to chit chat, we have an informal get together at PJ's right down the road, so you can come over and we can talk further. Everybody's welcome to that. So first off, we'll talk about space weather. So let me stop sharing. And Patricia, did you want to introduce our guest? And yes, let me make sure we can actually hear you. That
Hello.
might be...
Yes, am I here?
Oh, yes, I can hear you. That's amazing.
Fantastic.
Okay, so
Awesome.
Patricia, I'll let you introduce them, and then we'll go from there.
Hi, everyone. The past few weeks in space weather has been truly epic. I don't know if any of you heard, but we got a lot of people got a nice show on Thursday night. I didn't feel like I could fully convey what all happened, so I have actually asked an expert, Dr. Joshua Williams.
Cool. Hello. Yeah, so as Pat mentioned, my name's Dr. Joshua Williams. I'm a space physicist at the University of Newcastle in Australia. So it's currently 6 a.m. for me, so thank you for having me. And I just thought I'd share a little bit about what is currently going on with space weather at the moment. Can everyone see the screen? I think so, yes. There are so many windows open at the moment. I've just got to make sure everyone can see the...
Yes, we can see it.
Yep. Cool. Fantastic. Awesome. So, yeah, right now, surprise, surprise, we are smack dab in the middle of solar cycle 25. Now, this is quite exciting for me because, as you can see, this solar cycle is already a little bit bigger than the last solar cycle that we had. So, if anyone's heard of the Van Allen probes, for example, uh, they were a set of spacecraft that were launched in 2012 to actually look at space weather, and that timed right about with the last solar cycle. As you can see, the peak of the last solar cycle was a little bit of a letdown, unfortunately, in the scientific community. But thankfully, this solar cycle here, with all of our fancy new gadgets, is shaping up to be a lot more interesting. Of particular interest and amusement, I always find, is that they often forecast it going down, but they've been forecasting it going down for several months now, even though it's very unpredictable. It keeps going up for some reason. So our forecasting abilities for this solar cycle seem to be a little bit broken. We're not quite sure what's going on, and it's giving us a lot of really good new information about what processes are governing this solar maximum. How does the sun actually work? But you can see here already 2024 is shaping up to have the most number of solar flares of pretty much any year in the last several decades. In fact, going all the way back to 1997, you can see here we've almost matched what we had last year, and it's only mid-October at the moment. Of particular interest is this little speck of dark red up the top here, which is the number of X-class flares. And particularly the number of flares we've had just in the last month has been absolutely phenomenal. So here, I've actually looked them up and listed them all here. Last month, we had 2 X-class flares, an X1 and an X4. And the way that we classify solar flares, for those of you who may not know, is just the amount of X-ray radiation that comes off the solar flare when it explodes on the sun. And the stronger it is, the more likely it is that there's going to be a corresponding coronal mass ejection, so a big burst of plasma coming from the surface of the sun, which then comes and whacks our magnetic field, causes it to move around and inject particles into our atmosphere. So last month was interesting. We had an X1 and an X4. And then this month, we're only, what is it? For me, it's the morning of the 13th here. And that's not even the middle of October. We've already had 5 X-class solar flares. In fact, one of them on October 3rd was an X9 that actually ranked as the 15th largest solar flare that we've ever seen. So very, very exciting for us. Now, this might be a little bit too much information for you guys, but as a space physicist, when I'm looking at the interesting bits of weather, it's how extreme were the effects of what we saw on the sun here on the Earth. And we've got this parameter called the DST, the disturbance storm time. It's basically how severe was the geomagnetic storm that was caused by the coronal mass ejection that we had last week. It caused our auroras. And you can see here in September, the DST was pretty middling, it went down to about a -100. A couple of times, these are probably corresponding with those X-class flares that we had. They released coronal mass ejections that, they might have been impressive, but they only glancingly blowed us, so they didn't really do much. And you can see here that -100 DST, it's a moderate to intense storm sort of thing. That's relatively decent. But the one that we had just then, the storm that caused the auroras that we could see over Thursday and Friday, depending on the time zone that you're in, caused a drop in the DST down to about just over -300, almost -350, which actually puts it in the realm of a superstorm. And this is why you were able to see auroras as far south as Texas. And in my case, we saw people posting pictures of seeing these as far north as Townsville, Brisbane, that sort of thing. And if we want to relate it back to the other biggest storm that we've had this year, which was the May storm, this wasn't quite as strong as the May storm, but it was certainly getting up there. The May storm had a peak DST of around about -420 nanotesla, which again puts it in the realm of superstorm, but not quite as intense as some of the other ones that we've seen historically. So this is comparing the last few that we've had to the one that blew out Canada's power grid. I don't know if anyone here was around to remember that or maybe experienced it themselves. That had a drop by almost minus 600 nanotesla back in the year that I was born. And then if we want to compare it to the Carrington event back in 1859, the one that actually allowed people to run their telegraphs without actually being hooked up to batteries, that would have required a drop down at about minus 1750 nanotesla. So the storms that we saw, very, very impressive. But in the context of what we've seen historically, they're up there, but we have potentially more wiggle room to see more extreme events, depending on how the sun's feeling over the next little bit. You can see here, this was actually the coronal mass ejection that caused our auroras to form. All came from this lovely little active region here that I don't think I've labeled. Oh, that was 3848 was the one that caused this. This was our solar flare, and this solar flare led to the formation of a coronal mass ejection. This is a GIF image from Soho, I believe, or Lascaux. And we've got this instrument here called Cactus, which actually allows us to sort of measure the outline of that coronal mass ejection as it comes off from the sun. And if you see what we call a halo around the sun when the coronal mass ejection happens, it either means that that coronal mass ejection is heading straight for us or heading straight away from us. And in this case, when Cactus actually outlines it for us, it's almost a completely full halo. So this is why it was able to cause the auroras that it did, because not only did it come from an X1.8 class solar flare, so pretty strong, but it was aimed straight for us or staring straight down the barrel of the gun. So we saw a drop down there of about minus 350 nanotesla. Unfortunately, we don't really look like we're going to see much more over the next little bit. The solar disk is, I wouldn't say quiet, but certainly not as energetic as we've seen. The two active regions that were causing all of these X-class flares, one of them's already gone around the limb, around the western limb, and then this one here, 3848, which caused our last set of auroras, has lost its delta class magnification, its classification, which is just its configuration of magnetic energy on the surface. We classify these sunspots based on how complicated their magnetic geometry is, how much north and south is in there, and what combination of it are there. Is it all, north on one side, south on the other, or is there norths and souths all mixed up together here? You can see that now it's a little bit more simple than it would have been a little bit earlier. So it still harbors a fair amount of energy, but it's not pointed straight at us, and it's also a little bit less energetic now. Not to say that it couldn't happen, though. We've still got a prediction of about 25% for more X-class flares. So I'm certainly hopeful that we see more of it in the near future, but we'll have to see what comes over the eastern limb over the next week or so. Okay, any questions?
Oops. Thank you so much for that presentation. I can show you the audience. And then here, did you have a question?
Hello, Professor Williams. I was just wondering if it's really the protons that do the damage when they to spacecraft and to electromagnetic systems on the ground, or is it really some sort of effect from the X-rays?
That's a great question. It's a combination of both. So anytime you see a coronal mass ejection, sorry, this is what I had prepared earlier, actually. You actually get several different effects happening all at once. So right as the solar flare happens, you see a burst of X-rays, because that travels at the speed of light. It takes about 8 minutes to get from the sun to the Earth. That can certainly maybe damage spacecraft, but doesn't really pose that much of a threat, because although these X-rays are, relatively powerful, it happens sort of all at once. It's just a sort of burst of, light to them. It can overwhelm sensors, but they recover relatively quickly. For us down here on the Earth, that doesn't really do much, except it does thicken the ionosphere, because it increases photoionization in our upper atmosphere. That's why we get HF radio blackouts, and why it can affect communications for us down here. Shortly after that, about 10 to 60 minutes after the solar flare, you get something called solar energetic protons. These are protons that are traveling almost at the speed of light, not quite at the speed of light. So they take a little bit longer than light to get here. And they can damage spacecraft because they're particles. They carry more energy, and because they're moving so fast, they carry a lot of energy. So certainly when we see these solar flares, if we expect that there's going to be quite a large solar energetic proton event, we can shut down spacecraft and protect them that way. Again, though, that doesn't really have too much effect down here, though, because our magnetic field actually shields us from the worst of that down here on Earth. Unfortunately, the spacecraft aren't quite as far in the field as we are. However, it is about 18 to 24 hours, up to about 3 days before we get the true effects of a solar flare with a coronal mass ejection. So the solar flare is sort of the explosion on the sun that can potentially release that coronal mass ejection. And when that big cloud of plasma comes and hits our magnetic field and basically does this, we get a lot of internal processes happening inside of the Earth's magnetic field where it actually energizes existing plasma populations up in the magnetic field. And that is actually what's most dangerous, both for us down here and in the spacecraft, because this is more dense than, the protons that can come from the sun, those solar energetic protons, and can potentially be even more energetic. So it's kind of like if you had a wave coming from the sun, the wave can be a little bit damaging. But if, suddenly you were caught in a storm and it was going to last for, say, a day or so, that can certainly be a little bit more of a worry if you're a satellite. When this magnetic field wiggles around, it can actually sit there and it can energize particle populations. We actually get what we call killer electrons being made faster and faster as it saps more and more energy out of the magnetic field. And those electrons, if they hit our spacecraft, can be quite damaging. So this is why in the most extreme events, it will be during the geomagnetic storm that comes after the solar flare that we potentially may have to shut satellites down. But during the solar flare and even that solar energetic proton event, we can, but it's usually pretty okay. Sorry, I hope that answers your question.
Yeah, Dr. Williams, that was great. There's actually a lot of interest and a lot of questions in the room here. Unfortunately, I kind of have a jam-packed agenda. So if you don't mind, could I have maybe Patricia gather any questions that people have and send them to you, and then maybe we could get the responses back that way if you're okay with that.
Yeah, sure.
Okay, well, thank you for getting up so early, Dr. Williams, and sharing that with us. It's really amazing to see how active the sun is and what a big impact it has on us. So.
No worries. Thank you for having me.
Thank you.
Thank you.
Oh, and there's applause. I'm not sure if you can hear it online. So.
Thank you.
See, and then I need to get this over here somehow. Okay, there we go. Cool. Okie dokie. And then share. Awesome. Okay, and next we're going to have Brooklynn come up and talk about a new comet that is in their sky. So here you go, Brooklynn. I'll let you take it away. I just clip that on you, or you can hold it.
Flip it? Hold it? I hold it?
Leave it the way it is.
How do I click it?
Nathan, can you put it on her?
Sure, absolutely. So we'll just
They're on my jacket.
put it right there.
Okay. Right here? Okay. Hello, my name is Brooklynn Levi, and I like to play tennis. Louder? Hello, my name is Brooklynn Levi. I like to play tennis, and I go to school at McAdams, and I go to robotics, and today I'll be talking about the new comet in the sky. This comet in the sky hasn't been seen for over 80,000 years, and the first ever people to see it are the Neanderthals. The former name of this comet is C-2023-83. This comet was discovered in January 2023. This comet is 44 million miles away from Earth. Mars is 140 million miles away from Earth. NASA said that it is believed that the comet came out of the Oort cloud. And what is the Oort cloud exactly? The Oort cloud is a shell of icy space debris that is in our solar system beyond Pluto. This comet is massive in size and length. It is 130,000 miles in diameter, and the trail is 18 million miles long. This comet will be visible October 12th through October 26th. The comet will get higher in the sky and harder to see with the naked eye. The best viewing time is an hour after sunset to the west, close to the horizon, and will move up over the days. This comet will not be moving like a meteor, but will be in one place. This comet will be the brightest comet in the next 10 years. Remember to look up in the sky tonight. If you see on this board, it will go higher up in the days, so you can only see with binoculars. That's it.
Very far. Let me get the mic from you.
Can you pick it up?
Yes. How do you pronounce the name of the comet?
How do you pronounce
I have no idea.
And next we have space news. So, Greg, you want to take this away? This is it.
How do we close this out? Oh, this is from. And we had two slideshows. That's okay. So space news, roughly covering the last month or so. We'll just focus on a couple of areas where there were kind of big stories. The first one is the mission called Europa Clipper. Now, this is a NASA mission, and it's going to Jupiter's icy moon, Europa. And we'll talk about why, of course. But briefly, it was discovered back in 1610. Galileo found it. It's a little bit smaller than Earth's moon, so it's not that different, but it is smaller. Key thing about it is it has a frozen crust on the outside, mostly water ice. And that is over a saltwater ocean, and which makes it kind of interesting because potentially there could be life in there today, not something like 2 billion years ago, but now it is possible at least. You know, if you got reasonably warm temperatures, you got a source of energy inside, there might be a radioactive core. They don't actually know that. That's something they have to find out. How do they even know that it has a saltwater ocean? Interesting question. Well, apparently they noticed that magnetic fields around Jupiter, which are very, very strong, are significantly disrupted by the presence of Europa when it goes through. And they found that out from probes before that have magnetometers, so they know that. And they finally concluded that there had to be electrically conductive fields. You know, basically, anytime you get electricity and magnetism, one way or another, you get forces and interactions with each other. And the other thing is that because of the strong gravity of Jupiter and other passing moons, basically the planet is kind of flexing, you know, and as a result, it's like tidal flexing, just like the moon pulling the oceans on the Earth. You get friction and that can keep things warm as well. And all that goes on, so they think there's a pretty good chance there could be life in there. So, I mean, it's possible. Now, they're not going to actually detect it directly, but they're just going to look for it. Now, the biggest thing about Europa, though, from a hazard standpoint, is extremely high radiation. Europa's orbit is relatively small, relatively close in to Jupiter. And as a result, it's really, really high. Jupiter's magnetic field alone is like 20,000 times that of Earth's. And so that, and there's charged particles coming out of one of the other moons, Io, and all that stuff just generates all kinds of radiation with the interactions there. So, but in any case, people say this is the most likely place to look for life outside of Earth in our solar system. We already know it's here. This is just a kind of a cutaway version just to show you that you got an icy crust, and that's what that outside, that's what that looks like. One thing they want to try to figure out is what does that brown stuff really represent? They think it probably came from cracks in the ice where every now and then water from underneath gets through with whatever other stuff is in it, and that might be what accounts for the brown. They don't really know. And then there's the ocean. They don't know how deep that is, and that's part of what they want to find out. How deep is that ocean? And it's assumed, just based on the overall density, which they do know, that there's rock and maybe a metallic core, but again, they don't really know that. They're hoping with a lot of instrumentation, with magnetometers and so on, they should be able to figure out a lot more about it. Now, as I said, the big question here is, are conditions suitable for life? And again, they're not directly detecting it, but what they're going to try to identify, their specific goals are figure out how thick that ice crust really is, figure out the ocean depth, and there may be subsurface lakes. And even in those subsurface lakes, there could be life as well. There is geological activity. You can tell that from that previous picture. There's all those strange looking cracks and things. And that pretty much says, that's not the kind of picture you get. Where is it? Oh, it's the next page, sorry. Yeah, it's that one. You don't get that from meteors. This is something that's going on inside the planet. So that's what they're striving for there. So the one thing they're hoping for, they've seen this on other planets or other moons, is you might occasionally get a crack in the ice. For instance, it might be opened up because you get hit by a meteor, or maybe just due to the various forces that you get a crack. If they get really lucky and then some part of the ocean underneath shoots up, they'll be able to sample it, because they're going to be taking samples of actual material. They're not just looking at it with spectrometers and so on. They're actually going to be able to analyze some of the stuff. That happened, I think it was Enceladus that went by, and they got lucky. They actually had a probe that went by a different moon, and it actually managed to fly through one of those plumes. So, they know this kind of thing can happen, and they're hoping it happens here. And
Have they seen plumes?
I'm not sure. I think maybe, but maybe are they big enough to be of any value? I'm not really sure on that one. But they are hoping to determine the compositions of the ocean and the surface. So how are they doing all this? Well, they have a variety of scientific instruments. Obviously, that's what the Europa probe itself looks like. They're taking images. There's optical and infrared, thermal. So they have getting a feeling of how temperatures are distributed. Spectrometers, they have the optical type, ultraviolet and infrared, which is commonly used for figuring out composition. And also mass spectrometers, where this is when they sample dust and particles in the general area. They can actually analyze those as well. They analyze magnetic fields. They have radar, including subsurface radar. So they, just like the way people have seen down, inside of Egyptian tombs and that sort of thing. You can see through the ground with the proper frequency and power in the radar, and various ways of sensing gravity. So they are looking at the surface and what's underneath the surface. And to really see what's underneath the surface, that's why you need to be there. You just can't tell that well from here. And as I said, they will be collecting, they're not only looking at the surface, they're actually going to be collecting gas and dust. They'll be close enough to do that. The spacecraft itself, it is the largest one that NASA has ever built for planetary exploration. With the solar panels open, it's about 100 feet wide. Those are the solar panels there. You can get a sense of the scale. It's not, it's not like skyscraper size, but they're big. There's people in that picture. There are 5 panels. You can see the 3 of them there. They're kind of folded, and there's 2 of those on the spacecraft itself. So that gives you an idea what it looks like. So the thing, it weighs about 6.5 tons, and well, there's a lot of propellant. The actual weight without the propellant is called the dry weight. That's 3.6 tons, and the whole thing cost over $5 billion. So this is actually a big deal for NASA. It's one of their very large scale projects. Most projects don't cost that much, or at least they try not to make them cost that much. Now, launcher, that was an interesting story, because originally Congress pretty much said you have to use SLS, the Space Launch System. But in 2021, NASA concluded that just wasn't going to work. Then they switched to the Falcon Heavy, SpaceX, for a whole lot of reasons. And they actually had to get an act of Congress to be able to do that. It's bad that Congress really sets constraints on design and a lot of our rockets, and that was one of them. A big issue is simply cost. Basically, SpaceX is delivering this for $178 million. At the time, SLS was estimated to cost $2.5 billion per launch. And now now it's more like 4 billion. You know, it's added up. They've done more audits and they've actually gotten a better feel for how expensive it really is. So it turned out that was a good thing. But there were other issues besides just the cost. Availability is a big one. SLS was not really set up for having a lot of launches. You know, the few that they were going to make and the manufacturing capability they had only supported the Artemis program going to the moon, pretty much. And so, you know, maybe they were going to set, you know, they were expecting to build one every couple of years, that kind of a thing. And there weren't any available. So there's risk on the schedule because SLS hadn't actually flown yet at that time. The second thing is from testing, they knew that they were going to get a lot of shaking from the solid rocket boosters. The SLS is the rocket on the left there, and the side, you can see where the big flames are coming out. Those are the solid rocket boosters. They apparently generate a lot of vibration, and they figured out from testing that actually the probe itself wouldn't stand up to that. So that was actually a big problem. So that would have meant they had to redesign the things and then remanufacture, and that would have added a lot of schedule risk and, of course, a lot of extra costs. So they figured it was an extra $1 billion to do that. So they said, okay, they can just do the whole thing on Falcon Heavy for under $78 million. Now there was, you know, as with all decisions, there's always some downsides. The downside here was SLS was a more powerful rocket, or it is a more powerful rocket than the Falcon Heavy. So the SLS, they could have just basically directly flown there and then done it in 3 years, which is pretty fast by interplanetary standards. The Falcon Heavy is not quite powerful enough to do that. What they have to do instead is fly by planets. Like they fly by Mars, they get a little gravity assist by getting pulled by the gravity of Mars and also accelerating when they're in close. There's the Oberth effect, it's called, allows them to basically get a little extra oomph out of their limited propellant. Yeah, it's a slingshot thing. You've all seen it on Star Trek when everybody stands there and they come in real close to the planet and they're all shaking and shaking and then I hope it hangs together, Scotty, that kind of thing. So yeah, you've seen that on TV. They're doing that, of course, and they're going to go by Mars and actually going to make a pass coming back past Earth again even. So it's both of those things. As a result, the next thing is it takes longer. It takes 5.5 years to get there. Which really is not that big a deal in terms of interplanetary robotic exploration. If you're sending people there, that'd be a problem, but you know, for robotics, not a problem. As a side note, it turned out there had been recently, until yesterday actually, a grounding of all the Falcon 9 rockets by the Federal Aviation Administration. But it turns out that wouldn't have affected this particular flight because it's licensed by NASA. The regulatory environment for rocketry is still really kind of up in the air when you get down to it. And who decides, it's not even clear who decides. Basically, if NASA really says, I want to be responsible for this, they get to be responsible. If the FAA says they want it, you know, then they fight. But usually if NASA speaks up for it, they do it. So it wasn't clear, but anyway, in this case, usually the deep space kind of stuff like this, typically NASA would take responsibility for those. And they would say, no, it's okay, you just go ahead. Now, when they get there, I was talking about the high radiation environment. This is a picture showing Jupiter in the center. The red zone shows the really high radiation area, and then the yellowish orange is you know, less intense. Now, Europa's orbit there, it's not the innermost planet, or moon, but it's, you know, it's inside that red zone. That radiation environment is really not good for, it's terrible for people. People couldn't survive more than a day there. But it's also terrible for, you know, instrumentation. And so they figured, okay, what they had to do, well, first of all, they're putting all the electronics inside of a big metal box to help shield themselves from that. And they had special radiation hardened electronics as well. So that they were trying to avoid all that. But even with that, they're worried about it. So what they're doing is they're having an orbit that goes around Jupiter, and they're just going to keep making passes around and around, each time intersecting the orbit of Europa and coming, you know, close, actually coming closer a little each time. And by doing that, that says they spend most of their time not in the high radiation area, and so they can recover a little bit. So there was a big scare about this, though. Up through May, they thought things were fine. Somebody ran some additional tests on the radiation that was there, and they found that the transistors that were used, the key electronic components, actually they weren't surviving. Even though they were radiation hardened and inside that vault, nonetheless, they were having all kinds of real problems. So they studied it and finally concluded that the transistors would actually heal themselves when they got outside the radiation, which sounds pretty bizarre. like it's damage. It's like it's damage to the crystalline structure of the semiconductors that are making up these components, but they kind of recover on their own, and especially if they're heated up some, even just to room temperature, because normally they're going to be colder out there in outer space. So now they refer to this as a form of annealing, which is kind of interesting because usually a lot of people have heard of annealing associated with metals. If you're gonna make metal a little bit harder, you heat it up. But the thing is that metal, you'd heat it up really, really hot, and above the point of where there's any kind of crystallization of any sort, and gradually cool it down. That's how that works. It turns out in semiconductor manufacturing, like the transistors, they have the same kind of thing. And the thing is, though, for that manufacturing, they have to take it up to 1,300 degrees Fahrenheit. So they're also referring to this as annealing, but it's obviously going on at a much, much slower rate. And I didn't really find a good explanation of why that is. But anyway, that's the wording they're using. But it's the same kind of effect. What happens is you heat stuff up above the point of crystallization normally, and it cools back down, and you get more perfect crystals formed as it cools back down. And apparently, just heating the room temperature, it does that much more slowly, but it's enough to help. So that's what they're saying. Anyway, so NASA recertified everything and said they're going to go for it. And they have plans, though, for heating the thing up. They weren't necessarily going to do that before, so they're going to heat it up to room temperature every time they're outside the radiation zone to speed up that recovery. So they're kind of crossing their fingers on this one because they don't really know. But otherwise, it would have taken, probably, a couple more years, and who knows how long it would have taken to redesign everything. And this way, they avoided all that. So the mission timeline. It was supposed to have launched October 10th. It may launch in the next couple of days. They have a launch window until about November 6th, where they can launch this thing on the orbit, and achieve the trajectory that they really expected. So they had the thing all packed away because of Hurricane Milton. They put it back in a building somewhere. And according to the reports, everything survived. So they're going to roll it out and launch it basically as soon as they can. It could happen fairly soon. It has to happen by November 6th. Okay, so anyway, once it's launched, as I said, it has to fly by Mars and then Earth again and get some speed boost out of that. It finally will arrive at Jupiter, in Jupiter's orbit, around April of 2030. And then it'll actually be flying by some of the other moons as well. Finally, it gets to Europa around 2031, and then they're going to make about 49 passes using an orbit, kind of like what we're showing here. They're going to vary it, and they're going to come in closer and closer, as time goes on. They'll get in as close as 16 miles, which is pretty darn close. So I've got a movie, but I think just on the interest of time, we'll come back to it if we have time at the end. And there's a movie put together by NASA. Okay, next topic. Probably a lot of you remember this. NASA had done a test of planetary defense. What happens if there's an asteroid out there that's heading for Earth? Now, of course, we all know that you hire Bruce Willis and he goes and blows it up. But, but we don't really know that that's going to work. So they decided we need to do something about this. So there was a project of NASA called DART where they basically smashed a spacecraft, that one on the lower right corner there, into the smaller of a binary pair of asteroids. The one they're smashing into is called Dimorphos. And the reason they picked that was if you smash into it and you basically, the idea was you change its momentum, you're changing its path. You could tell how you did based on the orbital, it's orbiting around the larger asteroid there, Dimos. And if you slow it down enough, it goes in and it changes the speed. You can't actually observe these directly. Our optics are not good enough. So all they can do is the same way they detect planets around stars. Essentially, you look in the area where you can just kind of see a blob of light. And when the smaller Dimorphos gets in the way, there's a dimming, of the light that's reflected off of it from the sun. And as a result, then they can tell what the period is. And so it is actually measurable. So if the period of the orbit changes, then they know they succeeded. So they did a head-on collision with Dimorphos, and that was back in 2022. The goal was to slow it down. So what that would do, by slowing it down, it lowers the orbit. And actually, to have a lower orbit, you have to go faster. So in fact, that speeded up the period. And it sped it up like 30 minutes, 31, 32 minutes, something like that. So it was quite successful. And they're pretty happy about that. But the thing is, they want to have a mission now to go back and look and say, well, what really happened here? By the way, interesting point here. You know, we don't really know much about asteroids when you get down to it. You know, there's several different types. This actually shows the actual pictures of what they look like when we got out there right before the crash. They managed to, you know, get good pictures of the things. This was the artist's conception of these asteroids before. I think the Didymos one was probably just a complete fabrication. The little one over there, Dimorphos, that one actually I think was taken from one of the asteroids the Japanese visited. I think Bennu or one of those. So that one is realistic in that it's at least another asteroid, but it's not this asteroid. And again, I'll show you how to flip back and forth. That's the artist's conception, and that's the actual pictures. You can't really trust artist conceptions, but because they reflect what the beliefs are at the time. And I'm not trying to make fun of, you know, astronomers. It's just simply that, you know, space is big and far away, and you don't know what stuff really looks like until you get there. And so you make your best guess. Now, what actually happened, though, is that instead of being a hard piece of rock, Dimorphos in particular, was probably what's called a rubble pile. That's official technical terminology, by the way, the rubble pile. Meaning it's just mostly a bunch of loose boulders, probably mainly held together by gravity and not stuck together like glue, you know, like clay on Earth or something. They're just pretty much held together by gravity, they think. The impact, when this spacecraft ran into it, it blew 2 billion pounds of rock off of it. That's out of 9.5 billion, so it's not even that much, but it was enough to change it. That debris formed a tail stretching for thousands of miles. It looks like that, actually. That's actually the first man-made comet, or human-made comet. So that when people see that in the future, we can say, we did that, you know, thank you. But that's proof that we can do something. You know, we can actually change the way the universe appears. That's actually a good thing from the standpoint of planetary defense, because if you think about what happens, okay, suppose my left hand here is Dimorphos. You smash into it and slow it down. If it just gets absorbed, then basically you slow it down and you change the kinetic energy, they kind of cancel out. But if material gets ejected, it shoots off. That adds additional force. It basically amplifies the effect of just running into it. And it turned out it did. It's actually like 4 times what the effect you would have had just from the billiard balls, you know, it bumped into each other or something. Anyway, so that's what it looked like after impact. That was about 2 weeks after, and there was no comet tail there before.
So you're saying that the impactor went into Dimorphos, and on a real short time scale, there was a pause. And then there was an explosion, like a cannon coming out.
Yeah.
That's what happened.
Well, I don't know about how long that pause really would be. I mean, it builds, the second you start hitting, it has an impact. But yeah, obviously, it has to go in some. So there's
when it slowed, when it hit us, when it slowed down, that impactor basically vaporized, had to have, and maybe that means there was a hydrodynamic explosion, a hydrodynamic shock wave that formed, and that's what blew the material back out the hole, and it was like a giant cannon.
Yeah.
And so that was what caused the second jolt. The first jolt was the impactor hitting,
the second was all that
slowing it down. But then the second jolt, and possibly the larger one, was the hydrodynamic shock wave effect.
Yeah, it's basically, like I said, it's almost a factor of 4.
Yeah, from the energy being deposited. Kapow!
Yeah. So anyway, the idea of, and by the way, you said, oh, of course, we're assuming that the craft got vaporized. Well, we don't really know that. So that's the kind of stuff they want to find out by going back and visiting it again. So the goal is to analyze the aftermath. You know, what does it really look like? They had pictures on the way, because not only did they have pictures of the spacecraft itself, but they had a little CubeSat off on the side taking pictures of the whole thing. But you know, it didn't last very long either. So they don't have any information now, and that's what they want to get. So they want to find out, well, first of all, even the mass of the main asteroid, they don't really know that well. By circling it and really analyzing, they can figure out its mass a lot better. Then they'll know better what the impact was on the system. The shape, what shape is this asteroid in anymore? You know, for instance, if it really is totally a pile of rubble, it could have changed shape completely. If it's a hard rock, it might just have little impact crater. And you know, the real answer is probably somewhere in between. There's probably a bunch of boulders that got rearranged a bit, you know, and some that didn't, and we'll find out when we get there. But they're going to study the magnetic fields, the gravitation. They're going to analyze the compositions, because this craft not only has itself, but it also has two little additional CubeSats that they're going to go on land and take samples. And so they're going to actually try to get a better understanding of what's there. I'm going to highlight one thing in the picture here. This is from the European Space Agency. It's their project. What they did was they kind of assumed that back before this mission, most people thought most asteroids are hard rock. You know, they knew about the rubble pile kind of theoretically, and maybe they knew about some, but they always assumed that. You notice they draw this nice straight line to that little impact crater right there. That's what they were assuming was going to happen. They were assuming there'd be an impact crater. And of course, that's probably not what really happened. And how do I know they assumed that? Well, they made that a lot more explicit in this picture, where they drew a line showing their analysis remotely going right to that same hole. So the chances are that is not what actually happened, and that's what they want to go see. And I'm not making fun of the space agency. Again, you don't know what's out there until you go. So anyway, this one, another case where the launcher actually ended up being a SpaceX Falcon 9. And the Europeans are quite upset about this, I mean, because they like to have their own space program. But it was kind of controversial. But on the other hand, the Ariane 6, which would have been the rocket to take it, wasn't ready yet. They'd stopped building the Ariane 5, maybe a little too early, and they ran out of rockets, so they didn't have much choice. They had to go to SpaceX to do it. And you know, that's typical. The Europeans have kind of fallen behind in launch, but they're still quite active in a lot of other things. Like once you're up in space, there's all kinds of stuff they're doing, and this is an example of that. They're building the spacecraft that are going from Earth out to places like this, as are the Japanese and others. It's not just us. It is actually controlled from Germany. Their operations control. Presumably, that's after launch. I mean, the launch is certainly going to be run by SpaceX. But once their craft is separated from the Falcon 9, it's all done out of Germany. So the spacecraft itself, 2,400 pounds. It's 5 feet across in the core, and then 16-foot solar arrays on either side. So it's not as big as the other one we just looked at, but it's still pretty big. And then there's a couple of shoebox-sized CubeSats that are going to go and land. And the plans seemed a little fuzzy. At least one of those they're saying is going to land, but maybe both of them eventually will. In all cases, they're not doing that first. They're going to circle around and get as much data as they can. Finally, they'll land one or more of them, and they might even land the main craft itself. They've left that up in the air. That's why I put question marks in some of this stuff. They will be analyzing the mineral composition and so on. And this is just another view of the same kind of thing. Before they land, they're circling around and they're going to coordinate. And, they're playing up that using laser communications between the satellites, they'll really be able to control a lot of experiments. Certainly, a lot of the ones related to gravity and that sort of stuff. You can just shooting radio signals and seeing how much gets absorbed. You can learn quite a bit. Timeline. It was launched. It was launched on October 7th, so it's on its way. And it was a Falcon 9. Now, that was an expendable mode. They had, the way the Falcon 9s work, if you want to get the most power out of them, you treat them like a normal rocket. You don't try to recover anything. Because as soon as you try to recover the booster, that said you had to save some fuel behind to be able to land it. And if you land it in the middle of the ocean, you use a certain amount. If you take it all the way back to Florida, then you use even more. And so this is going the other way. They're saying, no, this needed the full power in expendable mode. Now, this is another case where there was actually, when this was actually launched, despite the fact that there was a ground hold by the FAA on Falcon 9 launches, except for this one. And the reason is, well, the problem that they were grounding for was it was a second stage problem, where it was the re-entry. Basically, the engine misfired. Normally, you go up and you use the booster and it falls back and it goes back and goes back to either usually to a drone or maybe back to Florida. But then the second stage, normally it goes up, it drops off its payload, and then it has a burst of fuel to slow it down and then vaporize itself in the atmosphere. And it was doing that it didn't work properly. That's why they were grounded. But for this mission, that rocket wasn't coming back. It was going off into space as well. So they figured, okay, there's not a danger to people here because the second stage isn't coming back to Earth anyway. So it didn't matter. Normally, they come back to Earth into the atmosphere. Anyway, it'll get there. It will fly by Mars. It's actually going to purposely fly right by Deimos. I don't know how you pronounce that, but one of the small, there's 2 small moons on Mars, and they're going to really fly close to that and get some nice pictures. When they get there, it'll be 2026, and they'll maneuver around, do some landings. Okay, separate topic here, completely different kind of topic, and that's metal 3D printing in space. And you probably think, well, wait a minute, I've heard about 3D printing on the space station for years, and that's true. But it wasn't metal, it was plastic. And it turns out there's a reason for that, and that's just that it's a lot harder to do. It had not been done before. And yet, really, you'd like to have a lot of the ability to print metal. You want to bake a wrench, when you don't have one, it takes a long time for Amazon to get up there and deliver you a wrench. So you want to be able to make parts. And that's especially going to be important even going further on the moon. Again, it really takes Amazon a long time to ship you a wrench to the moon. You want to be able to make your own. So there's a lot of parts that are metal. They have to be. The plastic wouldn't be strong enough, or it wouldn't stand up to the high temperatures, whatever. So, and taking a step back, especially, this is another one of these European experiments, they're really into thinking about the future economy where you want a circular economy in space, where you send stuff up into space, instead of having it just come back and vaporize in the atmosphere, you'd like to reuse it. And that saves you the money of launching stuff if you can recover it up there. And this is just sort of a start toward that. Well, at least you can recycle some of the metal. On a large scale, you're going to need something much more than this, but at least it's a start on at least trying to make some parts, get some useful material out of satellites that are up there already. Anyway, as I said, actually back in 2014, they first started printing plastic parts, and they do actually use those on the space station. So they're going to do this with metal, though. They're going to print a total of 4. The reason they printed the first one in August, and there's still 3 more to go. So the reason that's why we're talking about it now is they're in the process of doing the second one. And what they're doing is they're doing it in parallel. They're producing the parts up there, and then they've already produced the parts on Earth, and then they'll compare the quality. When they finally bring it back down, at some point they'll bring these parts back down, and they'll run them through lab tests and see is the strength is good, is the structure is good, and so on. Are they accurately built? Who knows what kind of problems you have? Because you're talking about, in this case, melting metal, which is kind of unstable in gravity. It actually turns out to be kind of a hard problem.
And Greg, were the parts in the ground also 3D printed using the same equipment?
Yeah.
So they're just trying to see how it performs in weightlessness versus down here.
And
okay.
Because weightlessness, it's the microgravity. That is the big issue. Everything behaves differently. So for instance, well, let's talk about that. Well, a big one is that if you do an awful lot of the 3D printed stuff for metals right now is actually used a process called laser sintering, where you take metallic powder and with a laser, basically you melt it in little pieces, and you kind of go around and you build up the melted pieces, and then you have a lot of dust left over, and you kind of brush it off at the very end. You really can't do that in space. I mean, it's a mess. I mean, people are going to be breathing in pieces of little metal. It's just not going to work out too well. So they had challenges, and the other thing is that typically those machines are a lot bigger than the desktop kind of stuff where you print out your Starship models or something. It's a bigger deal. They're only going to manage, even though with a washing machine sized printer, they're only going to manage something that's about 3.5 inches high, and they're circular parts, but maybe 2 inches wide. But the big thing is the high temperature. A couple hundred degrees is all you need for the plastic. Here you have to get to 2,200. There's fumes, all kinds of fumes come out of this. You really can't have that in the closed environment of a space station or a moon base or something. So, as I said, you can't use the powder sintering. So Airbus is the one actually building this. What they did, well, first of all, is sort of the obvious solution is you put the thing in a big sealed box. Okay, so at least you try to capture all those little loose parts of metal and fumes flying around. You take care of it inside of a sealed up box. The second thing is that they're using wire, basically stainless steel wire. Traditionally, most of the 3D printing that went on in the past here on Earth is mostly with powder. Whereas the plastic ones that most of you probably are more familiar with, you typically feed those with wire, cable, plastic sort of thing. So cable. So anyway, that's what they're doing. They decided to build a process based on stainless steel wire, and then they're melting it with a very high powered laser. The melting area is about 1 millimeter of 0.04 inches. Anyway, the other thing they have to do is they have to purge the atmosphere, which would have oxygen in it. They have to get that. And that's why another reason for having the sealed box is you want to be able to pump in a pure nitrogen environment. That way you avoid oxidation, rust, basically. What it looked like, basically you just had this box on the outside. You can see that in the center here. They have a cassette of wire, and they melt it right here. And this, again, unlike some of the things where, like, you think of, printing cartridge in a printer or something, actually, what moves is the table that the parts are mounted on, and it's called a motion table. And then it's fed in, and there's a, I had a video of that. Where did it go? There it is. Okay. So the table itself is rotating. There's the fixed position where the the high temperature metal is being melted and added to that particular surface. So that's what it looked like. That was done on Earth. That's not the picture from space.
Are those full test samples?
They didn't really talk about what they are. I mean,
That's what they look like, though.
Yeah.
That's like one of the first steps you want to do. Once you generate a part like this is full on it.
oh, okay. Well, that's probably why it's that kind of a shape then. The very first test, I didn't really mention, the very first test was just to print some S's on the table itself. And it took them many, many months to get that to be successful. And finally, there's a lot of calibration that had to be done apparently. They just don't know how to model this stuff that well. But now they're at the point where they are actually doing this. They did produce the first part and they have 3 more they're doing. Okay, next item here is SpaceX, an update in general. Kind of a funny question to ask, but what business do you think SpaceX is in? Most people tend to think of it as a launch business, and that was certainly true. They build rockets. Although, strictly speaking, they build launch as a service. They don't really sell that many rockets. They're not really a rocket selling company. They're really a service selling company. They sell you the service of transportation, and they're providing it. That they kind of have to do that because they're reusing their rockets. So they don't want to really sell you one. They want to sell you the service so they can keep reusing it. But on the other hand, they have the Starlink project, which is satellite-based internet. And I kind of picked a couple of pictures just to represent this. On the right, you have Starlink. This is the phase 1 where there are 1,500 satellites crisscrossing, basically covering every spot on Earth. And that's only phase 1. Right now, there's well over 6,000 satellites, like 6,400 something. So it's a lot denser than that, but there are different shells at different altitudes and so on. But that's a good symbol of what does Starlink look like and do. And then over here, you have the rockets business, but here you're emphasizing the fact that it's a service, and the reason that they're so successful is they're reusing their boosters, and they're landing them on drone ships typically. And if you can say, okay, so there's the 2 main parts of the SpaceX business. It just so happens that right now, the revenue coming out of Starlink has now passed the revenue coming out of the launch business. And actually, there's also what's called positive free cash flow. I mean, even accounting, basically, you look at, are you making or losing money on the operations? Even after accounting for that, you're spending a lot of capital expense, meaning you're buying a lot of equipment and machinery and so on. Even accounting for that, they're actually starting to get cash flow coming back out of it now. And this is the first year that's been true. So now this is actually all per plan. I mean, Musk said this years ago that the launch business isn't really big enough. We want to go to Mars. How do we pay to go to Mars? Well, the way we pay for it is we do some other stuff. Well, they did Starlink. And so essentially the profits, they made so much money, really, it's hard to tell because, there's a private company, but really they make so much money from the launches that they could afford to get through the initial cost of building Starlink, which is huge. And it's been like a $10 billion project. And you had to get that cash from somewhere. Well, they got that out of being the most successful rocket launcher. But now that Starlink has gotten past the kickoff point where it's actually running and making money, now it can start throwing cash back and start paying for Starship and all the stuff that's needed to go to Mars. And this was all exactly as laid out by Musk early on. Okay, we talked a little bit about the grounding already. That was the 3rd time in 3 months that it happened, this most recent one. Previously, back in July, there had been an upper stage failure, and then there was a bad landing of a booster. It collapsed. Probably the legs just weren't good enough because the thing was too old. It had already been up there like 21 times or something. So But this latest one, the upper stage, it had a misfire. The engine didn't fire when it was supposed to. And this was during the mission to deliver astronauts to the space station. The 2 astronauts, not 4, because they're leaving empty seats for a return next February, or the 2 that got stranded up there by the Starliner stuff. And so they delivered them, but it was really just the return of that stage. It didn't go back and land in the ocean where it was supposed to. It missed. So that was enough to flag it. And those are all legitimate kind of things. Those are the kind of things the FAA ought to be worrying about, is why didn't things work as they were supposed to? By the way, they just cleared that. I just saw that this morning. They cleared it, I guess, yesterday. So they're back in business now. It turns out they probably didn't miss that many launches, because the 2 that are, that are of immediate concern, well, one wasn't monitored by the FAA, and the other one didn't have a second stage coming back to Earth, so this didn't apply anyway. But there is a lot of scuffling going on right now between SpaceX and the various regulatory agencies, the FAA and the EPA. They're making 2 basic claims. One is that there's absurd environmental fines going on, and we talked about this last time. For instance, spilling liquid oxygen in the launch site, that one was just insane. I mean, basically the oxygen, which was originally distilled out of the atmosphere, went back to the atmosphere. And this is not pollution in any way. Clearly, it was something else, but it had nothing to do with pollution. You might argue that it's a OSHA violation of some sort. There's an increased risk of explosion in a high oxygen environment. But even that, the Atlas V's, they pour out hydrogen, when they're at launch. So that's an even much worse problem. And no one's ever been bothered by that before. And the other one is about the water deluge system, which dampens all the heat and vibration at the initial launch. That's basically drinking water, and they're being accused of industrial pollution. Now,
challenge the word for that second.
Okay.
Because a water deluge, that water runoff is going into a protected wetland.
Yeah.
And scientists said, look at the rebar, look at all this other trash that water pushed into the wetland where all of these endangered species are. And so I don't like the word absurd.
Yeah, and I was about to say that's more like a 90% kind of thing in my mind. It's not good. But, well, and let's go back to where these things came from. The reason, basically, they're saying this is industrial wastewater, and it's a real concern. If you're at a refinery or a chemical plant and you get a water leak somewhere, I mean, there are a lot of toxic, hazardous chemicals around there, depending on what went wrong. If you had a leak in the heat exchanger or something where you got really bad chemicals mixed in. There aren't those bad chemicals here. They're not. So it's not really so bad. It is just drinking water. It's not any different than rain.
I'd like to challenge that because, though, sure, drinking water is fine. But whenever you take a bunch of drinking water, and we're talking about swimming pools full of water, gallons and gallons of water, and you push them across a launch pad, you're going to pick up those chemicals you're talking about, the oil and all the other chemicals that are on the launch pad, and push them into the protected wetlands. And that's where the problem comes.
Well, first of all, the amount of water is a lot less than a good heavy rainstorm. So this is no worse than a rainstorm, which happens all the time, including right there. No, I mean, you're talking a couple swimming pools, yes.
Should the EPA fine you when it rains and water comes out of your driveway and pours into the drainage system on the street? Because I think that's kind of what you're getting at.
No, I totally disagree. You're taking a swimming pool or 2 worth of water, you're forcing it across a place that has, a flight line that has oil and other chemicals on it into an environmental wetland. Well, then why is the rebar showing up?
Oil. There's no oil. This is methane fuel. It's only a liquid because it's chilled to minus 260. One's 260 degrees.
So none of the hydraulics on the test stands have oil on them. None of the cars that are driving up to the launch site have oil or leak
There's
gasoline.
Almost no oil. Well, there's certainly nothing fuel related. I mean, everything there is a gas and atmospheric pressure. There has to be a little bit of oil here and there. Even the hydraulics, they mostly use the rocket fuel as a hydraulic thing also. That is part of the design of Starship, is they're trying to avoid anything that they can't get in Mars. Then they can pull out methane, and they think they can get hydrogen out of the water. They can pull methane out of the.
So I live by White Oak Bayou. I live in a subdivision. So every time it rains, there's going to be runoff and that runoff is going to run into the street, then run into the drains, and from the drains it's going to run into White Oak Bayou, or the park right there around 43rd Street. And, you know, that means that my entire subdivision would have to be shut down as a polluting site, because there are cars that drive up and down the street. There are the driveways, there's oil, you know, bits, a little bit of gas drains on the street. I mean, there are city trucks. I passed 6 city trucks pouring sidewalks in my neighborhood coming here on the way. And so it's like, the city will have to stop building sidewalks in my subdivision because it's a pollution hazard the next time it rains.
Wow, you have
I
sidewalks?
think, pardon me?
You have sidewalks? Wow.
Yeah, I know, it's a great deal, it's a big deal. But it's like, I think there's a question of degree that has to be addressed here. And then there's the notion of like, let's talk about Deer Park for a few moments and what's going on over there. And you're worried about, and we're worried about drinking water, which is even better quality, I think, in a way,
Well,
rainwater. And, you know, I mean, there's degrees of severity here. And I think the notion that the Starship water deluge system is real bad, it's like, compared to what? I mean, there are wetlands over in the Deer Park area. There's 2 or 3 bayous over there. And it's like, why is the legal whip being applied here and not over to Deer Park, or not even to my housing subdivision?
Yeah.
we're going to agree to disagree. Thank you.
Yeah.
It's a little selective.
Well, I mean, I think you're a little bit quick to dismiss Jules's point, right? Because it's sort of like the difference between having like rain fall on the deck, you know, and kind of run away, versus like putting like some type of protective stuff on your deck and then power washing it, which is like pushing those chemicals, you know. So you have like all these things that have been done to the pad to protect it from the flames of the rocket. You know, is that material being
licenses for that, for the DCEU,
Sure.
and from the federal government.
But-
Yeah, it's basically concrete. I mean, it's a fancy concrete.
Yeah.
I don't think it actually has a coating, because almost no coating would stand up to that kind of rocket exhaust anyway.
Yeah,
It's
but-
pretty much solid.
But I think in terms of looking at, you know, people say, you know, pure drinking water coming out of the deluge system. I mean, it is any materials that are at that launch site are now being pushed out away from that in a much different way than, say, regular rainwater.
In my
How is it different?
environment, when I wash my car in my driveway with city water, if I'm using city water and I'm washing my car,
Mhm.
that runs down my driveway
Sure.
into the city drainage system
Right.
right there, and it runs 6 blocks west
Sure.
over to White Oak Bayou, and it dumps into there, and they've got little turtles and little frogs living there, because I've seen them. And I've seen a lot of other people washing cars in my neighborhood, and the little turtles and the little fish and all that, they seem to be doing just fine.
I think it's a difference between personal and industrial scale. So, like, you washing your car is one thing, but if a car wash that serviced a whole bunch of fleets of cars opened right next to it and regularly power washed all of their crud into that one bayou.
There are 3 car washes in my subdivision, around the edges of my subdivision, and they are doing exactly.
Okay, and
This is an extremely exciting topic
Yes.
to discuss.
Yeah.
So I can see us having a whole
Yeah.
meeting just
Those two,
on this.
we probably
which
can't stay
kinda
on that.
need-
Well, we'll agree to disagree. Anyway, I'll stick with absurd. I agree that, okay, it's only 90% absurd in the case of the water, but anyway. Okay, the second claim is simply regulatory overreach, and that's that should they be regulating all this stuff, like changing the launch control center or finding a new storage tank? This is really a case where the company interests are exactly aligned with, you know, the people's, in that they want success. Yeah, and so what they're just basically saying is there's just too much red tape. And of course, yeah, I realize everybody always says that when they don't like the results, but I think they have a point here, that it's not the same as the normal industry when you get down to it. Okay, Next thing is, now this came up last meeting actually, launching 5 starships to Mars. It turned out actually I had just heard about the launching, of a starship. Somebody in the audience had already seen that it was 5, and it turned out, yeah, that's true. They still haven't really said what's going to be in those. That's the main thing. But what this is all about, keep in mind, is that there's only a launch window every 26 months, roughly every 2 years. But what does that really mean? That's on the assumption that you're doing what's called a Hohmann transfer, which is something that's illustrated in this diagram down here, where you're showing the Earth orbit and Mars orbit. And there's a period where if you launch at just the right time from Earth, you can actually intersect, where it's going, where Mars is going to be at that point. And you do that by having one big burst out of Earth orbit, and that's the one down here near the bottom here. And then you have another burst of thrust up here at the top. Basically, the first one throws you out of Earth orbit into an elliptical orbit, which would eventually come back, except that up at the second point here, you have another burst of velocity, and then you match the Mars orbit, and then from there you go ahead and land. So that's where that comes from. Basically, and the time is fixed. You're basically coasting that entire period. It's like a 9-month period, independent of the size of the rocket or anything. So this is just where people are saying, okay, you only get a chance to test this stuff every 2 years. Musk never really, or SpaceX in general, never really explained why 5. My guess is, well, the biggest question is, can they do successful landings there? Well, if you get 5 tries. If you have to wait 2 years between tests, it'll take you forever to get there. Maybe they'll land, maybe they'll be in orbit, and maybe what they'll do is they'll land one, and if they see that didn't work well, they'll change the software and the control programming to try something else. They really have not explained this, why 5, but it seems like a logical thing. If you only can run a test every 2 years, do as much as you can in that period. So probably they're going to be testing, they've said they want to test, can they land the things? That's the first. Because it's not the same as landing on Earth. It's not the same as landing on the moon, where there's less gravity and no atmosphere. You've got some atmosphere, so it's a little bit different. The gravity is in between, and the atmosphere is a little bit there. Now, so the idea is you send unmanned ones, and then eventually, if that works out, you send a crew in one of the following cycles every 2 years. Now, the goal, this seems pretty unlikely to be achieved, but the goal is, you try to keep in everybody's mind, is something self-sustaining in, say, 20 years. And I'm not sure many people actually believe that's going to happen, but it's good to have audacious goals. That's what it comes down to. People focused on it. But still, what are the payloads? We haven't talked about.
Just a time check real quick.
Okay, yeah. Okay, we're almost done here. So Starlink, anyway, that's the other half of it. Basically, the bright areas there are the areas that are using it. It's still relatively expensive. In the US, it'd be like $120 a month for broadband service. And that's why you see the developed world mostly has it, and places here and there, usually where they're out, without good infrastructure. That's kind of always been their market, actually, is places where it will cost a lot of money to put in fiber optic infrastructure. That's a good place to use Starlink. I guess I'll skip through all this stuff. Let's see. Okay, just some miscellaneous topics. We talked about the fact that because the Boeing Starliner had failed, and so they had to send it back without astronauts, they sent up the next mission with 2 empty seats so that they can finally return when that craft comes back in February. Some other things, the Chinese are starting to put up their mega constellations, like the equivalents of the SpaceX stuff. And what they found from the first few that have started going up is they're a whole lot brighter than the American ones. So their astronomers are getting pretty alarmed about that. It's not clear what to do about that, whether the Chinese will respond even if you complain. Well, there have been complaints, but we'll see what they do. At least SpaceX made efforts, to cut back on it. Next topic was a quick one. Vulcan Centaur, which was a new rocket, its second launch succeeded almost, in that it actually got the payload, which is just a dummy mass payload. It was really running it for certification purposes. But actually, the solid rocket booster, one of its nozzles blew off, so it didn't work as well as it should have. The one interesting one that just came up is China just landed its first reusable satellite. It's about a 7,000-pound satellite, of which 1,300 pounds is payload. Some American companies have already done this, like Varda, we've talked about in the past, where you send up you send up something that's basically a satellite where you manufacture something, typically crystals or something, where you can do it in microgravity, and it's much higher purity, fewer defects and that sort of thing, and you bring it back. And so the Chinese are now doing this kind of thing too. This is their first time they've done this. They were doing a lot of experiments. They're breeding plants and doing various science experiments. They weren't that explicit on what they're actually doing. Yeah. Yeah, which Sparta was the same way. They were landing in. Yeah, it's reusable. It's a reusable satellite, as are the Varda satellites. That's and that's a new thing. You know, that there's not. It's basically when you get to space manufacturing, people think, oh, we're going to go up and do it in a space station. That's incredibly inefficient because there's all this handling of landing at the space station, handing it off to people, installing it, people taking it, and then taking the products and sending it back. It's a lot simpler just to send it up in the self-contained vehicle, do whatever it needs to do, and bring it back, and then reusing the satellite. So that's, you know, you're paying the same amount for launching that amount of mass. It's just that it's a whole lot more efficient. So that's most likely the future of manufacturing in space. The lab experiments that we've done on space stations, but you know, manufacturing is probably going to be more this way. Yeah, it's short time. Yeah. No, it's all going to be for really high value stuff. I mean, it's not. You know, you're not going to make steel. You're going to make stuff that costs thousands of dollars a pound. So, but anyway, Chinese are getting in on that too. I think that's it. Okay, just upcoming launches. Europa Clipper, momentarily probably. The rest of them are all the same as last time. Blue Origin's about to launch their big rocket. Flight Test 5 originally had been delayed until November. It might happen tomorrow, but it's pending at final FAA approval. Everything is going ahead as if the launch is going to happen, but as I heard even this morning, there hasn't been any official approval yet. So that was held up. And its big things are catching the booster at the launch site and also basically much better thermal protection. Oh, okay, so it's probably going to happen tomorrow then. Yeah, that's yeah. Anyway, another lunar South Pole mission by Intuitive Machines in January. Dream Chaser, which is another way to get cargo, at least it's basically a space plane, getting it to and from the space station, to be determined. I think that's it. I guess we don't have time for the movie. So, okay.
I just want to just.
Okay. Maybe you should.
No,
I didn't prepare something on that.
Michael, thank you so much for coming. Michael Flores worked at the. I think he's going to talk a little bit about what he did, but
I got lots to say. So
public relations and NASA did the Artemis 2 crew announcements. That was.
can't give away all the good
Oh, I can't give all. Sorry. Okay. So
this is
and
yours,
we
right?
could just give you this mic. You're good to go. You just put it on.
Okay, so here's going back and forth with that, and there's a laser pointer up here.
Copy that.
And you got the mic?
Got it.
I'll take yours for questions.
Okay. And the mouse works.
Got it. I'm excited to be here today. Thanks, Nathan, for inviting me out. It's funny, I recognize a handful of people here, some from LinkedIn and some from like random events that I've worked with NASA that I think I've ran into a handful of people here. It's Nathan knows I like pictures for my LinkedIn. I got to look cool. All right. So he's going to, if you hear random pictures going off, that's why. I'm excited to be here today. Talk a little about what I do, what I did at NASA, some of my work. So I'll go over my background, how I got to NASA, work at JAC, and then the big topic I talk about with students a lot, and it's really interesting to talk to this group too about this, is communicating complexity. In this group right here, we can say things like ISS, we can talk about these big ideas, Europa Clipper, all this different random stuff, and like everyone here kind of gets the gist of it. That doesn't happen normally though. This is not a typical group, right? So how do we communicate the importance of complex ideas in a simple way that makes sense? And I'll talk about the whys and things like that too. And then for a few people in here may be interested in it, how I got a job at NASA and how you can get a job at NASA or in the aerospace community in general, what you can do to kind of set yourself up for that. And throughout this, if you have any questions, you need clarity, let me know. Just chime it out, raise your hand, scream at me, throw something, whatever works, all right? So my background, I've worked a little of everywhere. I've worked in nonprofits. I've done news. I worked at the Houston Press for a while. I've done the media, everything from, I taught myself photography and I've used it everywhere I've gone. Video work, I've worked at aerospace. I worked for JSC here in Houston. I worked for Marshall Space Flight Center, which is in Huntsville, Alabama as well. I work right now, I work in the energy sector in oil and gas. I've worked with legal through Chevron law. I was an industrial radiographer for many years, so that was terrible. And I worked in retail for a good chunk of time. I worked at the Texas Children's Hospital for many years. Energy again, education. I work with local universities a lot. That's how we met here. I was at Rice. I worked with Sam Houston, Lone Star, U of H, a few other ones. Actually, given this type of talks like this a lot. For me, it's really important to be able to have these type of conversations because going through college, I didn't always get this, right? And I'm still doing some college work and stuff right now, but I didn't get to talk to people who were in the know, were in the mix. I remember I only heard from one person, and it was the director of marketing for the Houston Zoo. Really cool, but you know, I've been in college for 6 years at that point. Like, what's going on? So for me, I want to be able to provide value in that way. So doing talks like this, talking with these kind of unique groups, talking to universities, is something I love to do. And then also government engagement. So I've worked with nonprofits right now and do some government engagement for local governments, helping them figure out how to communicate ideas, things like that, as well as through NASA. So my time at NASA, I did a little of everything. So I've worked as a public affairs specialist, and I'll get a little bit more into what that exactly is, but I'll go through a few of the things that I did. So you can see me up there in my bunny suits. I would work with the lunar labs, working with the samples, going there every once in a while. You can see up here on the bottom right, I'm posing for Getty Images right here because I knew they were taking that picture and I wanted to have the Getty Images down there, so I kind of posed for it a little bit. But that was inside the Orion capsule when they were building it out. Working with Steve Bowen, Jimmy Chan, working with the Vice President of the Space Council, me on the stage for the Artemis 2 crew announcement. I got to do a lot of really cool stuff at NASA. When you think about public affairs and communications, you don't necessarily think about this. You think of somebody sitting there writing press releases, or behind a desk, or maybe doing some media interviews or helping facilitate this stuff. The cool thing about NASA, or any aerospace industry really, is when you're there, you're involved in space, you're involved in science, in no matter the capacity that you're in. So for me, I put myself in positions where I could be as involved as I possibly could. So the big thing I love to do, have you seen up there in the VR helmets? I was a medical test dummy. There's probably a better way to say that. Basically, I got to work with the astronaut corps, and I worked with the health missions group. And what I would do is, this was in conjunction with being in public affairs. This was the fun aspect of it. So basically, before they would test the astronauts or some of the astronaut candidates, they would have someone like me come in, and then they would test what they were going to test on them before. So if it hurt somebody, it hurt me and not them. So basically, they're like, yeah, we screwed up with this guy. Cool, at least he wasn't an astronaut. So like, we're okay. And so I would go in, and I would do everything from VR setups to even little stuff like tasting the food, doing the food tests in the food labs. That was a lot of fun. That was easy stuff. But one of the funner ones that I got to do is, so I came in, they're like, all right, wear active clothes. So I came in, I sit down, they're like, all right, were you ready? And I go, I have no idea. And so they're like, how tall are you? What's your weight? I'm like, 6 foot, I weigh 220. They're like, perfect, all right, here. And they start putting electrodes on my head. They add weights to my wrists. I put a weight vest on, and they add weights to my ankles. And what they would do is I'd sit down in a chair, and they would set up basically like a little obstacle course for me. And so one of them was I had to climb up this, like the Orion capsule. I had to climb up the ladder, climb out, run over, climb up steps, grab a sandbag, run across sand, run to the other side of the trailer, put that sandbag down, pick up this sandbag, come back, run back down, climb back inside the ladder, go back out of the ladder, come back down, and run and touch the wall. And that was what it was. And I had to do that like 5 or 6 times in a row. And so they did it as a base, where I was completely normal, I would run through it. And they're like, all right, you ready? And they put all the stuff on me. And they would start, not literally shocking me, but they would shock me a little bit to make me feel like off balance and all off, and they would increase it as I would go. So the first time I got up, I'm like, here we go. And I go, oh, God. And they catch me as I'm falling over. And then I get going and get moving, like, oh, you did great. And I go sit back down, like, all right, that was the easy mode. I go, what? Okay. And then they strap more weights on me, and then they put more, and then they amp up the electricity. So by the end of it, I was getting up to, I had an additional 60 pounds on me, and I could barely walk, but I had to complete it. Like, I had to get through it, and they timed me for it. And what it was is they're measuring stuff for, the idea is how quickly from getting back from space can we then be effective. So if an astronaut comes back down, they went to space, they went to low Earth orbit, they went to the moon, they came back, how quickly can they get back on the ground, get out, do a task, and then maybe launch again? So the idea for me, the increasing electrical charges that they would give me, the more dizzy I was, the more weight I got, was measuring how far I would go out, maybe low Earth orbit, how long I would be out, or if I was on moon gravity, which is 1/6 Earth, or on Mars, which is 1/3. So the cool thing about some of the work I got to do here through public affairs is the work I got to do is going to be studied and worked on for the next 30 to 50 years, right? Because it's about studying how humans interact on Mars. And I'm just a dude that knows how to write press releases. And I got to be a part of some really, really cool stuff like that. I'll tell one other part of that was really cool. Being in media, right? I would get to go into the vaults that we had. And the vaults were all the areas, some of the vaults, like we had moon rock vaults, we have all these different temperature controlled special areas, right, on GSC. One of the vaults is where they keep all the original film and all the original photos from Apollo, from all the original stuff. Really, really cool area. You have to walk through certain levels of double doors, or one area you walk through this warehouse and there's just like giant metal box over there. I go, what is that? Like, Apollo files. I go, what? It's just in a corner of a warehouse over here. Like, yeah, don't touch it. And I go, oh, okay. And so one of them go in there and I go, so what all we got in there? And they go, well, we got, this, we got the original footage of here, we have all this. What people don't understand, a lot of the conspiracy theorists will get into this, like, why do we only see the same photos? Honestly, because there were a lot of really crappy photos before that. You see that one cool, so the moon shot that you guys have on your right here, that picture was actually taken like this, where Earth is here and the moon is here. And so we see it like this. When you look at the original photos though, there's like 30 blurry ones, one with someone's finger on it, that great shots, and then like 20 more really kind of cruddy looking photos as you go. The reason we only see a lot of these original ones is there weren't that many great photos. Like they didn't know, like we couldn't take a picture, we're like, oh, okay, let me adjust my ISO, my shutter speed. No, that didn't work again. They didn't, right? They go through a whole roll of film, they do multiple rolls of film, they get back and 3 of them turn out great, right? So I'm going in there and I'm talking to him about this. And then we have some of the photos. I'm like, so can anybody see these? Like, yeah, they're all online. You can see all of them right now. Like all of us right now can go get access to them. All of them except for that group over there. I go, well, you gotta tell me what that group is. Or you gotta tell me what that is, right? And they go, we don't put those up. Like you could probably put in a press request and get through it. It probably wouldn't get approved. What it was, I probably shouldn't tell you guys this, but I've gone way too far. So way back in the day, like the original Apollo astronauts, they were training them in the Apollo missions. The astronauts at the time didn't know it was a big deal. Like they were just a bunch of like cowboy redneck engineers who were like, I'll strap myself to a rocket, let's go. And they were the smartest people on our planet, but they were kind of, they're test pilots. If you ever met a test pilot, you understand what it is. Like these people were just ready to go. So one night, these group of astronauts or candidates at the time, they weren't even called astronauts, were at a bar and they got drunk. And for some reason they ran out, half of them ran out almost naked out of the bar. And at the time, there were a few smart journalists out there. And there were journalists out there waiting for these astronauts to come out. And they got pictures of them as they were running out. And so some smart public affairs guy got to the journalist and was like, hey, don't do anything with these photos. And they have the photos now. And NASA bought them from them and took them on. It's like that, all on the up and up, no like threatening. But we have like in the vault, like these random photos of astronauts. And like, yeah, we can't show anybody those. I'm like, yeah, it's fair because there's naked astronauts running out in the middle of nowhere. It's a really cool space when you work in public affairs. One reason I went to this area is when I was in college, when I first started college, I started taking astrophysics and I did, because I love space, right? Like we're all here because of that. I started taking astrophysics, I started studying this group, and I realized real quick that like that's not my jam. I'm like, I can't do this math. Like, and the life hack is no one's actually good at math. Like some people just keep going with it and that's all it is. Like no one's actually really good at it. But I didn't really understand it at the time. I'm like, so I wanted to still be a part of this world, but I couldn't necessarily be a part in the way that I thought or the way that I saw. But what I was good at is talking. And I can write, and I can do these different things, and I can engage, I can be on camera, I can do these different stuff. And so public affairs in the communications world was something that kind of jumped out at me as something like, oh, I can put my footprint here. And so I got into it, and I started to get on LinkedIn and learning more about this job and connecting with people and harassing people and finding ways that I could engage in this space. And when I landed in was the public affairs space. Public affairs is kind of a catch-all for a bunch of different stuff. There's your public affairs officers, what they call PAOs, and there's your public affairs specialist. I was a specialist. Your public affairs officers, if you ever have heard a voice from NASA, besides someone that's sitting on mission control at a desk, 9 times out of 10, it's coming from a public affairs officer. If you go to like KSC or JS or Kennedy Space Center, or the Johnson Space Center, the museums, and you hear the echoes from the announcements of launches, or you hear any of these different things that are going on, those are public affairs officers. 9 times out of 10, that's what you're always going to hear. It was really cool when I was at, I was down in Florida for a launch, and I'm walking, I got some time, so I went to the Space Center, and I'm walking through, and I hear a launch going on from shuttle. I go, hey, that's Rob. I know Rob. All right, and I can call Rob. I'm like, hey, Rob, I'm listening to you. Look, man. He's like, please turn that off. Like, all right, yeah, fair enough. And I hang up. But you hear this stuff all the time, and these people that can announce, and if you ever see somebody that's on camera, 9 times out of 10, either there's like an astronaut or something there and a public affairs person behind them, behind the camera, but don't say this, shaking their head, doing these different things. These are what these people do. And so you do a little of everything, right? So press releases, news and media, mission control, NASA media, any of the videos that you ever see, any of the graphics that come out, you'll see it from people like this. And not just public affairs people that work in the comms area. NASA has a phenomenal history of working with commercial and contractors to do a lot of the work. When I first started at NASA, I was a NASA contractor. I worked with a company called Media Fusion. I was the communications lead for Marshall Space Flight Center. And then when I came to JSC, I came on as a public affairs, which is directly for Uncle Sam, right? Working directly for the government. But any of the stuff you see, that's why I recognize a few people in here, because also I would go work events. So everything from like Comic Palooza to Space Day at the Capitol, or going up to DC to do something, I would be there representing NASA, being able to talk and communicate, dealing with people who come up and say, I know it was all fake. And I go, sweet, I'm not going to talk to you. Let's go ahead. I'm going to talk to somebody else now. Stuff like that, community engagement, commercial aerospace, exhibits was a really, really cool, fun area that I love to work with. Exhibits was the people who ever dealt with any of the artifacts of NASA. So somebody comes back from space, a shuttle tire comes back from space, and we don't need that anymore. We can't just like give it away. So that becomes a NASA artifact. And the exhibit teams gets to deal and figure out where that goes. So it's working with colleges, working with Smithsonian, working with different people like that. Everything from something like that to the controllers from Columbia, to extreme things of like shuttle tiles, to decommissioned telescopes, all kinds of cool, crazy stuff. That was a really, really cool area. And then photography and video, STEM engagement, all these different things I got to be a part of and work in some capacity, no matter where I went. It was a really, really cool job. Every once in a while, you guys will see me on TV from old broadcasts when they're talking about the new stuff coming up that NASA has footprints in, or you'll see random photos like that of me in the bunny suit again, looking at the original Apollo moon rocks as they came back. Really cool area, a lot of fun, and something you want to think of when you think of somebody who works in the communications field. Now with this, I got to do really cool things. One of the biggest projects I got to work on was the Artemis 2 crew announcements, which is really fun because when they came to us, they say, hey, Artemis 1 went good. It took forever to get out there, blah, blah, blah. It's the most tested rocket ever because it sat out there, went back to the pad, went back and forth, did all these different things, but it performed perfect. I was there for that launch, and it was something else. So Artemis 2 was coming around, and we're preparing for this. They're building the rockets. Like, hey, we got to announce the crew. So they came to us, and they say, hey, so we've got the crew, and we basically get in a closed room, and they're like, you can't talk to anybody about what's going to be happening here. And we got a closed group, not because it's like top secret information, but it's sensitive information, right? So we're in there, and we start planning out how we're going to announce the Artemis 2 crew to the world. So this is different because it's not just a like Texas thing, it's not just a US thing, it's a international thing. People from all over the world, especially because Artemis 2 was already announced and talked about that we're gonna have international partners. So how do we make this accessible? And the only direction we got was, we want it to look really big and like, make it cool, make it big. And we're like, okay. And so we went back and we started planning. Our initial plan, if you guys, I'll show some pictures in a second. Our initial plan was to have like these moving walls and like smoke come out, like people emerge, and, like fire and explosions. Like we were gonna go for it. They were like, go Disney World big. And we're like, we got it. And then we're like, here, and our budget is this, and they're like, go smaller. And so we kept getting Uncle Sam pushing us back, right? So we eventually landed on, we were going to do it on JSC property, but if you do it on NASA property, you have a lot of technical issues bringing on media, international folks. It's a pain in the butt, especially if they're just from Canada, getting them onto a government property is like, it's like a 6-week process, right? Like you go through a lot. So we're having people from all over the world come in, so it becomes complicated. So we decide to use one of the T-38 hangars. The T-38s are the fighter jets the astronauts train in. Really cool, super old. They've been around, they're the same jets that they used to train the Apollo astronauts, things like that. It's really cool. And they rebuild them, literally, from scratch almost every 100 hours or something like that they fly. They break them completely down, clean them, replace parts, and rebuild them. So they are like new fighter jets. It's really, really cool. Yes. So we get out there, we ask them to say, hey, we need this hangar. And so they completely gut it and clean it out. And again, I'm the lead for this, and I'm working with a few other people. So I have lead for majority of the events, and then I have my media production lead, and I have a few other people doing this stuff. So we're working with a large team, and we clear it out, we design what we're gonna look at, and then it turns into this, right? So we have every single living astronaut or active astronaut there, besides the ones that are on the space station. That in itself was crazy to be a part of. I tried to take a selfie with them like that. They didn't really like that. When you're like in the mix there, it's not a really big deal. But I'm out there, so we designed this massive, crazy thing, and we get to announce the new crew going back to the moon, to the world. It was super, super cool. This was probably the largest event I've ever worked on. Having all of them there, and the day of the event, I was wearing a jacket, and I could not take that jacket off because I had sweat all over me. So, and I'm on camera for half the day. So they're like, why don't you take the jacket off, relax? I'm like, I can't. They'll all see how nasty I am right now, and I think I'm smelly. So it was a really, really cool, it was a very long day on this field right here. So that first picture there, what you don't see is we only had that space for about 72 hours, less than that. So we had to completely put that stuff in, bring in external crews, do all these different crazy stuff in the span of 2-ish days, 2 to 3 days. The third day was the broadcast day, so 2 days really. Because it's an active space. So we went in there the day they cleared it out, and me and Jack Moore, my colleague, went in there with tape. And we literally put we're on our hands and knees. I crawled up and down that space, putting tape and measuring out every single spot that every single piece would go. Because that stage and every screen, the T-38s, the Orion test module on the side over there, the giant prints, all these different things had to go in very specific spots. So before we ever even did any of this stuff, it was completely mapped out. We had a computer generated. We went in there with tape measures and laser measures, and we stood there and marked every single piece. So on the day of, when the crew got there, they said, you're going to green tape, you're going to blue tape, you're red tape, you're purple tape. And everybody went in, and within that less than 12 hours, the stage was completely set. Because we had such a limited window. And so I stayed at a hotel across the street that night, got 5 hours of sleep, came right back over there and did that. And it was one of the massive events, and it was extremely successful. One of the other cool events, and this is with my Rice connection here, is the JFK 60th anniversary event. This was a really fun event. I got to work with a lot of the commercial partners and a lot of the different people that I worked with there. Massive events. At the same time was the National Space Council was having a meeting at JSC. So the team was like split between doing the JFK 60th anniversary, managing the vice president and all these different people. So I went from there, ran back up here, did some work with the vice president, came back, went back to Rice. It was a fun day. Now, NASA is pretty unique when it comes to stuff like this. You don't see any other aerospace company doing this stuff. And that's not to disparage them, but there's a very specific reason why. You don't see Boeing setting up and doing this stuff. You don't see SpaceX doing this stuff. You don't see Lockheed and all these different companies doing this type of work. And it's for a very specific reason. When NASA was founded, they founded back in '58, and they put in this act, right? And within the act, they put on there, to accomplish this, NASA will conduct a comprehensive set of activities to effectively convey and provide an understanding of NASA's work, its objectives, its benefits to target audiences, the public, and other stakeholders, including NASA's employees. Basically, at the foundation of NASA, they built in, hey, we need to talk about what we're doing, why we're doing it, why it's important to people, why it matters. From the very beginning. That's why stuff like this isn't really something that's like an optional thing for NASA. It is something that's built into the charter. If you're a NASA employee, you have a prerogative within your job code to talk about the work you do in an effective, creative, safe manner, whatever that looks like, to tell the public what's going on. And I know everyone loves a good, NASA Space Policy Act. So, but you go through this and it talks about it. It talks about talking with your own NASA employees, talking with people around you, and engaging with this stuff. So NASA is really unique, and it's a really cool thing. If you look at the little space science demonstration unit, that was one of the first demonstration unit vans that they had. They would drive to schools with things to put on the projectors so they could put up there and show people with the work they were doing. Where's your tax money going? And it started from the foundation of NASA. It's a very unique thing. No matter where you go, if you work with commercial companies, you work with anywhere else in the world, they don't have that prerogative. So NASA is going to be the only one that kind of leads the charge for that. It's a really cool thing. So getting into the meat of this, right? Fire away.
Communication under the impression where that NASA actually wasn't allowed to talk about what a good job it is. That's sort of like they're sort of prohibited.
NASA is strictly prohibited from selling services, right? Like you're a government agency. So when they come out to tell you something, they're not asking for anything in return. That's a difference between the commercial partners, right? SpaceX will talk about how cool they are. So that way, not only, but one of the reasons why is, hey, they want to get business. The Origin wants to get business. Hey, look what we just did. You want to be an astronaut? Stuff like that. NASA will come out and say, hey, let's talk about Europa. Let me show you what this is doing. This is purely science. I want nothing from you. Look at where your tax money is going, because you've already paid me. You've given me half a penny every year. Your half a penny went to building a $5 billion spacecraft. So NASA will talk about what they're doing, but you'll see the way in which they communicate is different from your traditional commercial partners because there's no return, right? There's no ROI on this. That also becomes challenging sometimes because when NASA goes to places, they can't necessarily pay to get in. We have to work with vendors and partners and stuff like that to see what we can do to be able to get into spaces to talk about NASA's footprint and what NASA's doing. So it becomes a little challenging while SpaceX or some of these people can come in and drop $20,000 without blinking to get into a space. NASA's like, hey, we're NASA, we're kind of cool, right? You want us here? And then we work for our partners to get in for it. So it's a little different, but that's a good point. So communicating complexity. This is the thing that I've gotten into arguments or discussions with people around this because it's a very passionate thing. Usually it's our engineers, the scientists that get into this because I have a saying, and it's not a new saying, it's not an original saying, but you're only as good as you can communicate. So a lot of times your engineers or scientists will come in and say, no, the work needs to stand on its own. They're like, cool, no one understands it. I don't know what this means. And if you want buy-in, you need us to understand it. And if you want to get really technical with this works great with students. There's been research studies on communicating science effectively. And the big problems that people will usually face when they go through it. So today we had this conversation here, right? We're talking about solar flares. We got, Dr. Williams talking about stuff. Brooklynn up here talking about the comets coming through and things like that. This group, that's great. We had our X-rays all day. Your general public doesn't understand that stuff, right? And it's not their fault. It's not from a lack of intelligence. It's just a lack of perspective and how much information they've been able to gather, right? We fail a lot of times, and the research study kind of goes into this, to identify clear and feasible goals for why we're communicating this. The catchphrase a lot of times, especially when it comes to hard science, is the public doesn't care about this. The public doesn't understand. And they don't understand how it affects them, and they don't understand the why. And that's the hard thing that we get into. And then also understanding your audience. And it's not just dumbing down what we're trying to say, but effectively communicating what we're trying to say where we get a buy-in from the people we're talking to. Today when I'm talking to you guys, I can say things like ISS. We can talk about coronal mass emissions. I can talk about astronauts and astronaut candidates and all these different things. Your Joe Blow on the street, though, who works in finance downtown Houston, why would they even care about that stuff? What's the buy-in for them? And what happens is people who work in science communications or work in science or engineering, they become frustrated with it because they should care about this. It's important to me. We just spent $1 billion on this, and they don't see the buy-in for that. That's always been a challenge for NASA because the conversation always comes, well, why we don't need to go to the moon. We have our own problems. We need to take that money and use it elsewhere. First off, Have you ever known the government to be really good with managing money? Right? Well, here's all of NASA's money. You think it's going to your pocket? No, right? NASA's been set up for a long time as one of the only purely science-based organizations everywhere, right? Any other aerospace company can come in, Blue Origin, SpaceX, whoever can come in and say, you know what? I don't think I want to do rockets anymore. NASA doesn't get that option. NASA will keep going and go forward and study science for the benefit of all humanity, is what they talk about now. A lot of times, too, in this group, it works a little bit better, but understanding people's point of view when they're communicating science. When we come in and talk about this stuff, when I'm talking to this group, I can use acronyms and names and talk about Apollo astronauts running out naked from a bar, right? It's kind of okay. I can't do that when I'm talking to middle schoolers or if I'm talking to a group at Congress or different places like that. Your congressional people who we're talking to who control the money, I have to talk to them in a different way. And a lot of times we'll speak from our perspective when it comes to this. I have the rule of the Nana test. So if you can't communicate something to Nana or your grandma, if she can't understand it, then you don't understand it well enough yet. And that's the thing sometimes, right? So the barriers to progress to how we communicate, right? We lack information a lot of times to actually fully understand what we're communicating. Sometimes we communicate what we know, and that's a lot of times why we can't communicate simply, because we don't know enough. When we get into it where we're talking about Europa, we're talking about, I'm just using Europa because we just talked about that, by the way. Where we talk about these different things, the James Webb Telescope, and we're talking about tungsten, or we're talking about gold foil, and blah, blah, blah. And like, why do we use this? Well, we use it because it's spacey. And then we move on. And we don't fully understand it enough, and we don't fully understand it, we can't simplify what's going on. And we can't simplify that, we can't have the buy-in for it. And that's the biggest thing that NASA or anybody that works in this area can't get to it. And then the biggest question that most people ask, when I was working with the public, it was always, what's the point? Why do we need to do this? And we can get to the grandiose idea, right? Like we all love to fall on that, like space. That's where we're supposed to be, right? We're pioneers, we're explorers. We need to get out there. Earth's not going to be here forever, right? And so we can get to that. But NASA has taken a different approach when we get into that, and most people should take a different approach. What this group understands a little bit better is every single one of us in here has interacted with something that was developed from space technology today, within the last hour. Their phones in our pockets, the air conditioner that we're feeling, right? NASA is really good at this by showing, you can go to these websites that we have on it. So NASA Home and City is a really, really cool one. I point people to this all the time, especially if they're like, what's the point? Why would I ever do this? Like, you know, the stuff in your own home right now, that technology was developed through NASA, through the aerospace field, through these different areas. And it's a cool thing because you can go to the website, NASA Home and City. You can click on it, and then you can go in there and like, oh, the blender was used, this uses this microchip from here, the lights, LEDs were developed from here, Bluetooth was, like my memory foam mattress, like all the different things. And then people can see like, oh, right away, my day-to-day life is affected by aerospace. That's really cool. And then the bigger thing too for business and industry is NASA is a government-funded thing, right? So right now, if someone in here went to the patent portfolio and NASA spinoff, the patent portfolio really, if you were in industry and you can go in there and you see a patent that NASA developed from government funding, you can say, oh, that's pretty cool. I wonder if I could take that and turn it into a business. And you can send a request to NASA and say, hey, I would like to access this patent. And they say, yeah, cool, here you go. And then you can turn and start your own business based off of all the stuff that right here. There's people that do water reclamation, water purification systems that were developed for the ISS. And they have full-blown businesses now working in impoverished areas doing water purification because of the open patents that NASA has. NASA spinoff is a really cool area to really show. Anyone here is probably, if you haven't followed the NASA spinoff like social media pages, you should check them out. But it shows all of the spinoff technology that's come from NASA. What we developed, like everything from phones to your cell phone camera, everything that's in there, like how we developed this stuff, all the spin-offs of technology that NASA developed. So why does it matter? Why should we communicate in a way that is effective, that's simple, that everyone can kind of buy into? The big thing right away is funding, especially as a government organization. We need money, all right? You gotta pay for stuff, you gotta pay for salaries, you gotta pay for telescopes, you gotta pay for all these different things, right? So being able to have buy-in and understanding from everybody around you, funding is a really big thing. Policy influence is something that I always had to deal with because I would deal with politicians a lot. So if I can't explain a simple thing within a minute to a couple congressmen or senators or whatever like that, and they don't have the understanding and the buy-in of what we're doing and why it's important, then the next time that funding comes around, maybe they don't put money back into NASA. Maybe they don't pass that policy that would favor having government engagement or government influence in these different areas. Educational outreach, media and public communications, those are always the big areas that I dealt with as well. And when communicating with superiors, anyone here who has a boss, which is probably everybody if you're working, how do I communicate? Because your boss doesn't always have the buy-in right now. Like I manage a team of people who are much smarter than me. So they come to me sometimes and I have to have them explain their work simply to me. And it takes some time. And so being able to do that in a stair-step way where you get the director of JSC, Vanessa Watch, has to come in and be able to, then she has to explain it to somebody else. So you have these engineers and scientists who would come to the public affairs team and be like, hey, I have to have a meeting with my boss's boss. Help me, help me communicate why this matters. And we sit down with them for a while. And by the end of the time we leave, we'd have a PowerPoint put together and all these different things. Then also, one that we don't talk about a lot is the ethical considerations. So if you can explain things simply, because like genetics, AI, climate, space, observation, all these different things, they sound really big, especially when you go to AI or genetics research. And if you can't explain the benefits in a macro way, then people suddenly have like this push off about it. And the ethical consideration, I don't understand why we need genetic research in space, so therefore we're not going to do it. And so if you can explain it in a simple way, clear, concise, and this is how it impacts you, suddenly there's that buy-in there. They don't care about all this stuff. They need to understand this. And so why it matters is really, really important. And there's a lot of different ways in which you can do that. I always start with why. Why it matters, how it impacts the person, how it impacts the individual. Why does it matter? So start with why and work your way backwards. How will it affect people around you? And there's a double-edged sword when it comes to NASA. NASA does pure science. There's no other organizations that really just do pure science besides some universities and testing, but they don't have to worry about funding because it's right there. Well, they have to worry about it, but they don't have to worry about it all the time, right? So pure science is really hard to explain why sometimes. Like, why do we care that there's life on Europa? Why do we care that there might be life in the Kuiper Belt or the Van Allen Belt? Like, why does that matter? And so explain the why behind that becomes challenging sometimes, because you can't be like, to understand the human experience. And you're like, that doesn't make sense to me. Like, okay, we'll work backwards. We'll come back to you on that one. But starting with the why is always what you need to do, even when it comes to simple stuff, funding, vacation times, I don't know. Start with the why on why you're doing this stuff. And when your audience, kind of what I talked about before, crafting the story is how I always work this stuff. You'll see the original Apollo. I put the Apollo press conferences in there. If you watch a lot of them, they're kind of dry, a little boring sometimes, because these were test pilots. If you ever compare these with the press conferences that we have nowadays, where I would sit down with our astronaut candidates and our astronauts, and we would go through press interviews together. And I'd sit down with them, and I would ask them and grill them questions. We'd go back and forth, back and forth, back and forth. And by the end of it, they could tell a story about their mission, tell a story about what's important to them. Simple language, not simple concepts. That goes to about simplifying things. The concepts can be complicated, but communicating in a simple way is what's important. And use examples. So I'll get to the fun stuff, right? So working at NASA, pros and cons. I love NASA. I loved working there. I had a daughter on the way, so I had to find a job that would allow me to fund my daughter, right? So I got to pay for a couple of kids and things like that, and I had somebody kind of headhunt me and bring me out to work in the energy sector. I plan on going back to aerospace eventually, but working at NASA is a little unique. So you want to get a job at NASA, how do I work there? How do I work in the aerospace industry? First and foremost, one of the skills that I always tell, especially students or anyone learning, learn how to talk. Public speaking is a learned and practiced skill. Like, I, by far, am not an expert in public speaking, but I've been doing it enough where I'm comfortable getting up here, little notice, and I can communicate effectively. Public speaking is a massive thing that can take you from being in the top 10% to being in the top 1% of performers, because you can communicate effectively your ideas. Learning how to get rid of the ums and uhs and learning your own style and your movements and all that different jazz comes in time, but it takes practice. People and project management is a really big thing that a lot of people who major in STEM fields don't ever look at. They look at it at the end when they're like having to get a job and having to do stuff. But the more you move up, the higher you move up anywhere, you're going to start managing more people and you're going to start managing projects. If you don't know how to manage people, you don't know how to manage projects, you're going to have a really, really hard time. Even simple stuff like what we have today. Managing, getting the people here, getting your speakers in line, getting all this stuff together. I know people who would have a full-blown anxiety attack if I told them they had to just, hey, set up a little talk and 3 weeks from now, they just would shut down. Like they just can't do it. It's no fault to them, right? They just haven't been trained on how to do that. So set yourself up to do that. Writing is really important, informal and formal writing. I went to Johns Hopkins University for a graduate program, right? So that's where my master's from. I learned research and analysis writing and all these different things and communication writing and stuff like that. It's cool, but it doesn't work for like a press release, right? Like I can write a doctoral dissertation, but writing a press release is completely different. And then people glass over real quick when you do that stuff. So informal writing that's not like social media, Facebook stuff, but is communicative in a personal tone is really something that a lot of STEM people have trouble with. Interpersonal communication, learn how to talk to people. Your HR department will thank you if you learn how to talk to people. We had a lot of trouble with, not a lot of trouble, we had trouble with people who would, especially your scientists or engineers, who would walk in, be very direct, and they would walk away. They didn't mean anything by it. There's no malice intended, but it came across really aggressive because they just didn't know how to communicate with people. They spent their whole life just learning their craft. And so to learn how to now communicate their craft was a completely different, hard skill for them to learn. There's a few other things in there. The biggest one that I always tell people, especially students, is build a resume like an astronaut. Now what I mean by that is if anybody here's ever looked up an astronaut and looked at their background, you're like, oh yeah, yeah, that makes sense. I worked with Jeanette Epps a lot. She's on the ISS right now. Really, really cool folks. Jeanette, if you look at her background, it is ridiculous. Like doctorate degrees, she worked for the CIA, she all these different crazy things. She is one of the most fit people too. You'd see her out there running around JSC, crazy people. And then you're like, oh yeah, she's an astronaut, that makes sense. Like, I don't even question that. And so when I work with students and work with a lot of people, like, all right, look at your astronauts, look at the people you want to be like and build a resume that's like, oh, that makes sense. Get those degrees that you need, get the training experience, work in the jobs that you need to work. And for me, it was the big thing about having those transition jobs. I worked at Best Buy for like 5 years. Loved it. It was a great company. NASA doesn't want someone from retail to go there. So I had to find a transition point where I could then go from there. I knew if I wanted to get with NASA, I knew my best in was to go through a contractor because those are the easier ones to get on and then go from there into civil servants. But I needed to have something in the middle that would allow me to look better on paper to get there. I wanted to be this. I needed these steps here. Transition, let me work in healthcare. I found a job working in the hospital system, communication, marketing specialist. I used that to leverage into my contractor role, which I then used to leverage directly into a civil servant role. And so now when you look at my resume, it's like, oh, that kind of makes sense. I see it. That's the progression there. So that's the biggest thing I always tell students. If you're wanting to work at NASA, for one, get on LinkedIn, start creeping on people who have jobs that you have. Look at their experience, look at their degrees, look at their certifications, and just copy them. just follow that route. Look at a bunch of them. Find what makes sense for you and find what you're good at. You can follow your passion, but follow what you're good at, and then you'll find your passion along the way. Because a lot of times we're like, oh, I'm passionate about architectural design. I'm not good at it though, and I'm not going to get good at it just like I was. I loved aerospace, and I loved research, and I loved astrophysics, but I'm not good at that. What I am good at though is talking about it. And I found my passion along the way where I can take complex information and communicate it in a simple way and have a buy-in. So if you can leave with anything, you want to work for NASA, just build a resume like an astronaut. You'll get there. All right, I'll stop there. That's kind of the end of my spiel. Thank you guys for letting me come out. I appreciate it. Yeah, absolutely. If you have any questions, comments, criticisms, I'll throw something, whatever. Not, that's great. That means I was perfect.
Comments? Anything? Well, Michael, I really wanted to I wanted to thank you for coming today. I'm hoping this actually starts with you. But I want to give you a little gift for coming out. And especially tomorrow, whenever you see it take off on the TV screen.
Oh, that's super cool.
I know
Thank
you're watching it at
absolutely.
7 o'clock in the morning. You can.
I'm up at 5, so that's perfect.
Oh, perfect.
Thank you so much.
So, yeah,
we'll throw it back in there.
There you go.
That's so super cool. Thank you. That's what I thought. I've seen them in person, but they were far away. So.
And it's made in China, so every purchase of one of these helps the Chinese space program.
Yeah, I'm gonna have to scan that just in case. You purchased it though, right? So all right, we're good. Then my money's safe. Yeah, I'll give it back to you.
Okay, thank you so much. Thank you. I did want to go back to one slide that Michael had here, and that is the skills one. So you can actually develop all these skills right here in this club. You could come up here and speak. There's opportunities for that. Project management, we did a Comet Palooza event. We did the Science and Engineering Fair of Houston judging. We've done other people management. Definitely a wide variety of personalities and people and interest levels here. You get a lot of practice. And then interpersonal communication, and then networking. So if you're interested in developing these skills, this is the place to be. So thank y'all for coming.
So Michael, would you, I appreciate if you could sort of speak to members of the audience about how it is not necessary to be a scientist or an engineer or mathematician or something to be in NASA or contributing to the program, that NASA really needs people with all sorts of skills and talents. And really, they're just looking for people kind of with the dedication to do that.
Absolutely. You have people in there. Like I said, I worked, the exhibit team to me is a good example of that. Exhibit team was full of people who were graphic designers, artists, writers. We would bring in poet laureates. We'd bring in all kinds of different people to do these different projects like this, who were not just, hardcore, who didn't have their master's degree in engineering, right? But they had an understanding of it. That's the biggest thing, though, is to have at least a surface level understanding of what's going on, because the tough part is when you are talking to somebody who, in this group today, we talked about some heavy topics, space weather, x-rays and stuff like that. Now, if I were to take that information, I need to take the information and communicate it to a different audience, I'd have to completely change about what we talked about today. But I need to understand that in order to then talk about it somewhat. So you don't have to have this deep, innate understanding. You don't have to be able to project, rocket trajectories and know what, delta V means and all this different stuff like that. You need to have an understanding of that on a surface level one. But yeah, you need people all over the world, all over different types, artists, engineers, scientists. We need also maintenance. You need all these different skill sets that you have to have for this
Scuba
world.
divers, I was sort of surprised when I found out that NASA needed scuba divers.
Scuba divers, I work with a lot of them. I'm actually good friends with quite a few of the divers right now. The scuba divers are really cool people, and they do a lot of really cool stuff. The NBL is awesome.
Have you come to?
No, and I was just going to second what Michael was saying. No, one of the things we talk about a lot of times, hi, my name is John. I work at JSC, and I work for the NASA's Office of STEM Engagement. And we communicate a lot about the different jobs that are available at NASA that you don't have to necessarily be an engineer or a scientist to do. Diving is one of them. I know a lot of the divers too.
Cool people, right?
Yeah, they are. But, from food scientists to people who know how to sew and create, you have those people that are putting together the spacesuits. So you need people that know how to handle, materials and fabrics. So just from every sector that you can think of,
you can do that.
I look at NASA as being like a microcosm of society. There's everybody's needed. So from every job profession that you can think of is available at NASA. So
the cool thing that I like right now, especially with OSTEM, that I wish I had when I was in my teens, I never saw that. Right. Now we see that. Now we get to talk about, hey, we need seamstresses, like hardcore people. Yes. These people are no joke.
Yeah, and they're working with materials that's like a swatch of it is like $2,000.
Exactly. I never correlate. When I was 17, I never knew any that existed. All I knew was astronauts, engineers, scientists. Same. And I'm like, I don't fit into any of those. What do I do? I got to be a freaking fighter pilot. I got glasses. That won't work. All right. So where do I go? The great thing is that your office, I worked with you. I recognized you.
I know.
No. And so the great thing with the office now is we're able to talk about this stuff. And it's actually hey, you can do anything here. You just got to try.
Well, I think we'll go ahead and wrap up the meeting here, but I wanted to encourage y'all to hang around afterwards and chit chat here. And then if you want to hang out, we could go to PJ's, just literally right around the corner, and chat more there. But thank you again so much for coming.
Absolutely.
And thank you all so much for the participation and the engagement. It was really good to have all of y'all here. And if we could just maybe take a selfie real quick. or a group picture before we go. We'll go ahead and put the, and if you're online, maybe you could turn on your cameras and we can just put them here in the background, I think. Yeah, like this. Okay, so if you're online, just go ahead and, that did not work. No, I'll just do a selfie. Yeah, I'll just do a selfie.
You're jumping in it.
Okay. Let me try one more time. I think the cord may have. Let me just try that one more time. Oh well, nobody online's on the picture, so that's okay. Smiles. I got everybody. Well, thank you all so much. And now I'll go ahead and just disconnect on. I mean the cord got disconnected to like the second display, but that just happened like right now. So I'll just leave.